Hi, my name is Sebastian McKenzie. I'm going to be talking to you about this thing, Babel. So my talk title is Babel, Consolidation of the Tools. You're probably thinking, like, what does that even mean? Well, I'm going to be explaining that to you, what Babel is, the future of it, and its role in the JavaScript ecosystem. So as I said, my name is Sebastian McKenzie. I go by SEBMCK on Twitter and GitHub. I also go by this weird teal cat on GitHub. When I close GitHub issues, it makes me seem nicer and less of a jerk. That's actually the only reason I have it. And I've also recently joined Facebook on JavaScript infrastructure to work on some of the stuff I'll be talking about today. So start off with some history. Babel used to be a project called 6 to 5. I started it in October of last year as a learning project. So I realized that there was a lot of stuff that I didn't know, like how compilers worked, how parsers worked, very basic computer science sort of topics. And for those of you who don't know what 6 to 5 is or what Babel is, so 6 to 5 was is a ES6 to ES5 transpiler. So you might have heard of this thing called ES6 or ES 2015. This thing allowed you to compile your ES6 code into ES5, so you could use new language features today in older browsers without having to rely on browsers to support them. There was a problem with this name, 6 to 5. ES6 to ES5, what about when ES7 lands? Well, it had to be renamed to 7 to 5. But what about when ES6 is commonplace? 7 to 6. But ES6 was renamed to ES 2015, ES 2015 to 5. So naming a project after like a version and a year that is continuously changing is actually a really, really bad idea. And so to combat this, 6 to 5 was renamed to Babel. And with this transition, it had an expansion of focus on Babel as well. So rather than just being for transpiling, 6 to 5 became just a more general purpose JavaScript compiler. It lets you do stuff to JavaScript. I'll go into a bit more about that later. So here are just some stats about how Babel is going today. There's over 5,000 commits, over 2,000 closed issues, 85 open issues, 119 contributors, and 338 releases. Meanwhile, the Babel website is getting 20,000 page views a day, and NPM around 1.5 million per month. Wouldn't surprise me if Laurie sends me a bill for that. And Babel gets 0 downloads. I'd like to keep it that way. Yeah, so Babel is a very young project. It's not even 12 months old. So 338 releases, 365 days in a year. Sometimes I push multiple releases a day, which, so yeah, it's matured very quickly given the time span that it's existed. And it's also used by a whole bunch of companies. A couple of weeks ago, Facebook.com was actually completely switched to Babel. So if you're skeptical about using Babel in production, then just take a look at all the companies that are relying on it in production today. So in order to understand Babel, you need to understand code transformation. So what is code transformation? It's actually a pretty basic premise. So you put JavaScript in and you get JavaScript out. The output JavaScript is inferred from your input JavaScript. So it can infer what your code means, what it does, and then use kind of contextual information to generate some output JavaScript. So how does that actually work? So we have some source code, and we need some way to manipulate this. Like how would you even begin to kind of deal with source code? So we need a stable and reliable data structure to represent this that we can manipulate. This data structure is called an abstract syntax tree, or AST for short. So with that previous code, we would turn it into a tree like this. So it's a group of deeply nested objects that expressively define each syntactic component of the source code. So each property of these nodes contains metadata about what it represents. And this may seem intimidating, this really complex data structure, but a more easy way to visualize this is just via a graph. So each element represents a node. And an even easier way to visualize this is just via a list. There's a whole bunch of ways to kind of visualize an AST since it's just a tree. And so yeah, so great. Now we have the source code in a reliable data structure that we can easily deal with. There's a whole lot more to that. So these are the three distinct phases of Babel. So there's the parser, which turns your source code into an AST. It's that data structure I talked about just then. And then the transformer, which manipulates that data structure and transforms it. And then the generator, which turns that AST back into readable code. So let's start off our first journey at the parser. So there are two stages that are gone through in the parser. We have lexical analysis that turns the code into a stream of tokens, and syntactic analysis, which creates this AST from the tokens. So first up is lexical analysis, where we turn the code into tokens. But what is a token? So we have this input source code, and then we categorize them into these token categories. This isn't a comprehensive list. It's not all the tokens. It's just the ones that appear in this snippet. So here, each part has been identified to be of a certain token type. And so here on the left, we have a list of them all. So foo is an identifier, and we have a punctuator, a number, punctuator, string, and then another punctuator. So now that we've split up each part of the source code into kind of individually what it represents, we need to somehow determine what sequences of these tokens represent something. We use this through a process called syntactic analysis, where we turn these tokens into that tree. So here's an example. So we just have this class declaration. We tokenize this into this list. And so now we have a list of what each piece of that source code represents. But how do we derive meaning from this? How do we tell what sequence represents what? So let's say I'll just use this pseudocode-ish method example. So we'll step through each line of this. So let's initialize our parser state. So the highlighted token on the left is the current token. So it's the current one that we're dealing with. And the highlighted line on the right is the line that we're actually executing. So here we start the node, we construct an object and add metadata to it, such as the current position in the source code. It could be used for stuff like syntax errors or source maps, so it points it back to the original location. So now that we've constructed our node, we continue to the next line. Now this expect method would ensure that the current token matches the token that we expect. So if the current token is in a class, then we would throw a syntax error. But luckily it does, so we just advance the next token. So now we're at an identified token, and we're going to pass that as the class ID. And so we run that pass identifier method, which adds an ID node to the class node. And then we again advance to the next node, and we check to see if this class is deriving from another one. So we check if the current keyword is extend, the current token, sorry, is extend, and we go to this branch of logic. And so we advance the next token, and then we pass this superclass as an expression. Then we'd move to the next token, and we'd begin passing the class body. So this would check like the curly braces and pass the methods and class properties inside of the class. And then finally, we would finish the node, wrap it up, give it a type, give it an end position. And then now we have an AST that looks something like this. So this is kind of fairly straightforward. We can see the start and end properties that represent the position of each node in the original source. So the class declaration at the start of 0, so it was the very first node in the source string. And so this would then be represented in like this simple graph. We have a class ID, the superclass, which is represented by the other identifier, and then we just have the class body. So now that we've covered parsing, it's time to move on to the next layer, which is the transformer. So again, these are the two main focuses of the transformer. We need some way to traverse this tree, so to go to each node in that graph and do stuff with it. And then we need a way to infer what a node actually represents. So traversal. So we need some way to visit this tree and conditionally apply operations on these nodes. And so in order to do this, we'll introduce a concept called a visitor. This controls the traversal state as well as controls how to deal with specific nodes of specific types. So for example, given this graph, so we have a visitor and we have an AST and we need to crawl it. And to do this, Babel employs a depth-first pre-ordered traversal algorithm. I had to search for that since so many words. And so it would do something like this. So it would just go through each one. Now the visitor would just be calling a bunch of methods on each object. And then those methods that it would be calling might replace it, might remove that node. And so the visitor is just responsible for doing stuff to each node of the tree. And so, yeah, we'll just go through it entirely like this. But visiting a node isn't enough. We need some way to tell what a node actually means. So if we just, for example, just visited that function expression there, we would have absolutely no idea, like, kind of what it means. We'd know it's just a function, but we're not quite sure how it appears in the source code because you might want to conditionally apply operations in certain contexts. So we do this through a process called static analysis, where we infer what a node does by how it looks. And so we discern information contextually from the position and placement of all the nodes. So one example of this is type inference. So say we've got this code represented by this tree. Now we see this happening, and we want to see what the resulting type will be of that addition. So it could be a number or a string. We want to statically determine what that possible type could be. And so as you may know, the result of an addition in JavaScript will either be a string or a number. It's a number if both the left and right values are numbers or a string otherwise. So we check the left-hand side. Is this a string? Well, bar isn't declared anywhere in the file. It could be a global, so we just aren't sure. However, we can determine that the right-hand side is an empty string, and so this addition operation will always result in a string. So this is a very basic example of type inference, but you can kind of see how doing a lot of these operations can kind of bubble up on a much larger scale. And static analysis has very kind of practical implications too, especially with transpilation. So here we've got this array destructuring declaration. We need to transpile this. So this is ES6, and you might want to run it in IE6 or something. So you need to compile that down. So it's quite straightforward. We assign the right-hand side to a temporary variable, and then we just assign each index to the bindings contained in the original array pattern. But this is kind of a dumb transformation. It'll be the same for every single, so the 1-2 array, no matter what that is, will always result in the same kind of output. But we can actually unroll this in the case of destructuring an array on the right-hand side. So if we can see that 1-2, if that part is actually an array, then we can actually unroll it into something like this. So now we can be completely confident that it's as simple as possible. A lot of what Babel does is there's a lot of kind of edge cases that simplify code as much as possible while having the same effect at runtime. So to do all this, Babel actually has a separate data structure that's decoupled but tied to the AST that it uses to do some of these transformations. And this is the concept of a path. So this is a way to get bidirectional flow between an AST that's reactive and very stateful. This sounds like gibberish, but I'll try to explain. So I've got this AST, but it's unidirectional, so information typically only flows down. There's no way to get access to the parents if you just have a node or the ancestry. So for example, say you pass a reference to this function expression, suddenly the rest of the ancestry is lost. Now we could store a property on this node, so just add a property to the object saying that this is its parent, and then you can walk up. But what if a node appears in multiple hierarchies? So you might want to reuse that node, and so you can't have multiple parents at the same time. And yeah, so you might want to have multiple parents at the same time. So now with the function expression has been replaced with an identifier, so it's been replaced with something else. So what we originally wanted was just to have the node that was the initializer to a variable. But it's been replaced somewhere else in the source code, so now our reference has been lost, basically. We still have a reference to that function, even though we want a reference to the identifier. So how do we solve this? How do we deal with applying operations to the relationships rather than just the node itself? So let's just flatten one of these identifiers into just a flat list. So as I said before, it only goes one way. But what if we introduce the concept of a path that represents the relationship of a node relative to its parents? So here you can see where a path is, it has a connection to a parent and a child, and then you can go up, you can go sideways, you can basically go how many ways you want. And so this path just represents, a relationship. So like you might have a brother, they might be a person, but they might be named George or something, but you don't care if the name's George, you just care that they're your brother. And so I guess that's actually a really bad metaphor. So yeah, it just represents relationships. It's also reactive, so it's reactive to changes, so if something changes then it gets updated. And so you can kind of imagine this as a tree on top of a tree. So here, instead of the tree representing a node, it represents a relationship between nodes. So the concept of a node path is an extremely powerful concept that allows you to be reactive to tree changes and have lots of transformations operating at multiple times and just have them work together seamlessly. And one of the ways in which this is beneficial is Babel employs something else called contextless replacement, where basically it allows you to reuse the same bit of transformation logic in multiple different scenarios. So here we just have a simple array destructuring assignment, and so we can exploit this pretty easily to something like this, where we just call calculate coordinates and we set x and y to the return values. But this is in a statement position, so it's in a statement list. But what about at an expression position? So this is something we need to take into consideration. So when you're evaluating this assignment expression, the value that's the first argument that's passed to do something needs to be the result of calculate coordinates. It can't be anything else. And if you use the exact same transformation logic that you used before, you would get something like this, which doesn't really make any sense. It's invalid JavaScript, because in JavaScript, statements and expressions are different things. But Babel knows how to interchange between the two. And since Babel understands JavaScript and its semantics, it turns it into something like this. So it retains the original result, so it makes sure that the code works as it should, using the exact same piece of transformation logic, since it can determine how to change between the two. So enough about transformation, let's move on to generation. So here are the two phases of the generator. It infers the style of the original code, such as like indentation or what kind of string quotes you use, and then uses that to generate the code back out based on that tree. So it collapses the tree back into source code. And then, code generation turns the tree back into source code. I'm not going to go into any detail on this, but feel free to find me and ask any questions if you're curious. And so this is kind of an overview of the entire flow that Babel goes through in determining, in compiling code. So AST, it turns into an AST, and then the AST goes back into code. So enough about how it works, kind of what the future has in store for Babel. Since I've kind of explained how Babel has become much more generic, and there's nothing really specific to any of these concepts that I've explained that is specific to transpilation. It can be applied to much more things. So yeah, let's talk about the future, which seems to be a recurring theme of the conference. So this is a list of all the internal Babel transformers. So there's quite a few. Most of these are ES 2015 to ES5 transformers, but there are quite a few more general purpose ones in there. And these are all the community plugins that people have written. These do all various things, from minification to optimizing code for specific frameworks. So yeah, there's a lot. And eventually, all the ES6 transforms that are in Babel will be removed, and they'll be put into plugins. So when you use Babel, you will just be using like this bare bones thing that you just throw plugins at. I guess it would kind of be similar to Grunt or Gulp in that regard, where you just out of the box it does nothing really, and then you just feed it plugins to get extra functionality. So yeah, the future. So it's time to wrap up. So I thought I'd cover some rough points about what's in store for Babel in the future, specific areas. So a big one that I see is dead code elimination and minification. So the current state of the art for minifiers is actually pretty terrible. The fact that you can run multiple minifiers over the same code and it somehow gets smaller. So if you run uglify over code that's being compiled by the closure compiler and it comes out smaller, kind of shows that the tools are fairly weak and they all employ kind of different tricks. And so I'm confident that like a minifier built on top of Babel using these transformation APIs would be much more efficient, since it allows you to do kind of really complicated transformations very easily. And so that's definitely something that I'm keen to explore in the future. So another is constant folding and static evaluation. So this will allow Babel to meta-interpret your code ahead of time. So there's certain parts of your code that can be determined at compile time. So it doesn't actually have to execute your code to determine what it's always going to evaluate to. And so this may slow down compilation when you're compiling your code, but it could possibly lead to massive wins, both on the minification and performance side. And so the last is static analysis and linting. So linters are kind of iffy. It seems weird that developers love automation, but a lot of the problems that linters tell you about can be automatically fixed. And so a lot of the core concepts behind linting are employed already by a JavaScript compiler like Babel. In order to transform code, you need to be able to analyze it. And linting is basically just analyzing code and throwing an error when it encounters something. So there's a lot of kind of concepts behind a lot of these tools, like minifiers, linters, transpilers, that they all share the exact same concepts. And having one platform to do those all on, so if there's like a new language feature comes out that you want to use, you kind of have to wait for every single part of your stack to support it. You have to wait for your linters to support it, your minifier to support it, and basically all the other tools that you use in your development stack to support this new syntax. And hopefully, I hope for Babel to become that kind of base platform. So once Babel supports it, anything built on top of it, like a linter or a minifier, automatically supports it. So I'm super excited for the future of Babel and the future of JavaScript in particular, and I hope you all are. Thank you.